Today we're going to present on our Ecoat and ANS for the future paint shop as it relates to GHG Scope 1, 2, and 3. So how we kind of break this up, we have 4 primary focus areas. Productivity, which is basically your footprint and how big that footprint is and what you can do to mitigate that footprint. Powertrain, we had a great talk with John this morning, kind of talking about how BEVs, HEVs, NEVs, PHEVs are all kind of driving what this looks like for all OEMs, not just Chinese OEMs, moving forward within the paint shop and what the paint shop's going to have to look like to accommodate these. In terms of sustainability, this is obviously a big issue with everybody. And it's going to be something that we talk about when we go through a technology walk a little later on how we have to re-engineer these products from the beginning so that they do reduce your carbon footprint, so that they do meet the 4R standard, so that they do reduce water and waste, even with Ecoat, which is 100% efficient, really, but also lowering VOCs and HAPs. I know HAPs isn't kind of a big thing right now in the US, but it's huge in EMEA, and EMEA drives a lot of what we do in Ecoat. And then manufacturing and paint shop of the future, which we'll touch on later, and we also have some great colleagues giving a presentation later that's going to talk about even further development as it comes into 3-wet and 4-wet technology. So here's just a few of PPG's recognitions in terms of sustainability. We love Barron's. EcoVadis scores silver. Obviously, we have a little ways to go there. But what we're going to talk about really is the Sustainability Leadership Award. We won it a few years ago on EPIC 300 technology. And what we're going to talk about today is the sustainability next gen of that technology. So in terms of our sustainability targets, we're just going to touch on a couple of these as they relate to my work and Lindy's work. The big one being 50% reduction in Scope 1 and 2, 100% reuse, recycle, and recover. Again, Ecoat, you can recover most of it, like almost 100% really. 5% annual reduction in spill release. This is a big one for everybody. Reduced water. So we, just like all of our competitors and even our Chinese OEM competitors, reduced water is a huge ask. And we have a lot of people who spend a lot of time just looking at the math of that. What does that mean? What does it mean to us? What does it mean to our customer? What does it mean to the end user? And we'll touch on that a little bit today too. And then one of our big ones that we're always committed to is our 15 million in giving back to communities, as well as our sustainability, which not just Pittsburgh or Detroit, but also our communities where our sites are. So the paint shop and how it relates to Scope 1, 2, and 3. So what PPG kind of did is they said, okay, let's assume 70% of our Scope 1, 2, and 3 comes from the application and 30% comes from the materials. Where I sit in the PPG value chain, I focus on the materials. So how can I get that 30% reduced? Where does that reduction come from? How do we measure that reduction? And how does the end consumer, OEMs, look at that reduction in their technology? So that's what we're going to kind of talk about today. So I'm going to cover the Ecoat section. Lindy's going to cover ANS. So in Ecoat, we're basically going to take a technology walk. We're going to talk about how we kind of had to re-engineer our approach, which then requires a re-engineering of the product, which requires re-engineering of the resin. And then we're going to talk about how we move through the value chain of getting the benefit out of the re-engineered process. So in terms of low temperature expanded bake Ecoat, where it stands in the can, it still has to be an Ecoat, okay? High edge, good throw, good corrosion, pretty indestructible. You can put anything on it. You aren't going to lose adhesion. It has to do what it's always been, but it has to do it better, more efficient, using less water, higher solids, and everything that goes along with that. And then the value outside the can, this is where you're going to reduce your energy consumption, you're going to reduce your emissions, you're going to reduce water usage, and we want faster cure. And we'll kind of talk about the math because we are going to include the math in that, where faster cure means different things to different OEMs. So the product. Basically, we took a technology and we said, okay, it's a great technology, people love it, but we have to make it more sustainable. And because sustainability means different things to different people, we basically have to start from a base. And we want that base to function with the best efficiency we can get, and then we can start delivering additive packages to specific OEMs that have a higher standard. But we want this base to be more sustainable than anything that we've ever done. So we have to give it an expanded bake window. We have to look at a low consumption of solids per vehicle. We have to look at no tin. We have to look at compact process and thin film pretreatment. We have to look at the appearance because we pride ourselves. PPG always prides ourselves on Ecoat appearance. And then we don't want to add CapEx. We don't want to slow down your line. We want to give you the ability to speed up your line so you can put more parts on, and then reduce biocide usage. Nobody likes adding biocide on a tank. So from the beginning, we have to re-engineer a resin. So in typical Ecoat formulation, you basically have a droplet. It hits the panel, it flows, it goes to the bake oven, and you start the cross-linking process. You cannot start the cross-linking process before you've optimized your flow, because if you do, you don't have edge or pinhole coverage, and there's a slew of other things you just won't get. So you're on a seesaw, right? If you're a formulator, we both started in the lab, you have to get off the seesaw. So how do we do that? So we basically changed how the resin is going to deposit on the film. So we don't want a droplet and then it flows. We want the resin to hit the panel and start flowing, because you're reducing your bake window. You're reducing your bake temperature, which means you're going to start curing this thing a lot faster. So that's pretty much how we address this from the beginning. And here you can see a traditional or an initial prototype of where we kind of started with this, and you're looking at the roughness, where we didn't achieve the flow we wanted before it started to cross-link. So we had to make some changes, and you can see here with our modified resin, you're able to do that. So now you have a flowable material that'll cure when you want it to cure, and you'll be able to get the performance that you want. So what comes next? Your curing mechanism. So to do this, we have to start looking at blocking agents, how they're blocked, when they're released, what temperature are they going to be released at, and then how do they orient themselves quickly. So once you're able to optimize your cross-linker to your polymer, you're able to do your cure test. Now, because we all started in the lab, the easiest way to do this is just solvent rubs. You just sit there and you rub it, and you're like, hey, I've got the cure that I want. But the more scientific way to do it, and to really kind of understand that the resin is doing what you want it to do, we look at rheology and we look at TA. So in terms of rheology, how does it flow? And we always want to make sure that we're maintaining rheology, because our customers don't like when you kind of start messing around with that. That's basic. So how do you achieve the same rheology, but changing your bake portfolio? And here you can see on TA, you can see that your bake is staying pretty much the same, but at a lower temperature, you can achieve the gel content or the gel rating that you need. So therefore, you're curing this a lot quicker and a lot lower temperature. So what's the benefit to the customer? You get a whole slew of things. You get reduced biocide, you can reduce sanding, which affects bullseye, reduced water, reduced cleaning, your oven filter changes can be less frequent, and no CapEx. And we don't want to slow down your line, we want to help you speed it up. Now, there's not a one-solve solution for everything, and everybody knows it. If you work in production, you know it. So in terms of electric ovens, you're pretty much not going to notice a difference. You'll notice the difference in a gas oven. But what people really care about is the math. So we take a gas oven and we lower the temperature 15 degrees. You'll achieve a reduction of 11%. However, if you reduce your oven time by 5 minutes instead and keep your oven temperature the same, you can get a 13% efficiency. So this becomes really critical to parts, and it's why parts and tiers love this type of technology, because they can just load the line more and they can fill the line. And you can even do this with big parts at your IC, right? So your industrial, your cabs, your John Deeres, they do the same thing. Now we can move to compact process, because this technology fits really well into compact process. So if you're familiar with the zinc phosphates, it's an old technology, but it's a workhorse technology. And if you know zinc phosphate, people love it. But it takes a lot of tanks and it takes a lot of dips. So about 5 years ago, everybody went to the Zircobond, which is like a thin film pretreatment. A lot less tanks, a lot less dips. But the big thing, again, is going back to that scope 1 and scope 2. How do we reduce our carbon footprint? Compact process. We can shrink tanks, we can shrink dips. So again, it's just all part of this system to help everybody achieve what they want to do while costing less and not causing too much chaos in production. So in terms of the paint shop's solution, we've covered compact process. Lindy's going to talk about the low bank body shop options for A&S. And then we have the commercially available 3-wet and 4-wet processes. And again, our colleagues are going to do an amazing job of talking about their low temperature cure alternatives to these products later today. And I'm going to turn it over to Lindy. Let me shut this off really quick.
How do you turn this? Changes. Just click that way. Oh, that's easy enough. Okay. Can you guys hear me? Okay. Yeah, I sound very loud. That's good. Thanks so much, Paula. So I wanted to talk a little bit today about the work that we've been doing in the adhesive and sealant space, partnering with our Ecoat team to make sure that we can also get that expanded bake cure as well as maintain some of the other performance properties you would want from an A&S portfolio. All right, so I think as all of us are aware, there's a lot more that cures in that Ecoat oven than just the Ecoat, right? So there's also the adhesives and sealants that go along, as well as some other components of the car. So here at PPG, we wanted to make sure we were developing a broader portfolio of products so you could really enable those productivity and cost savings. So within the body shop itself, there's a wide number of adhesives and sealants that are applied before the Ecoat process. Anti-flutter technologies to help with panel vibration for some of those outer panels, structural and semi-structural adhesives, things like that. We have current product lines today, Core-Seal, Core-Bond technologies, but we needed to make sure we were adapting our portfolio and innovating to keep up with these new market requirements and market trends. The higher productivity, the lower bake temperatures that Paula mentioned. We're also seeing some needs for increased manufacturing flexibility. So as we're starting to see new substrates come online, heavier metal segments, especially for electric vehicles, there's new substrates we need to make sure we have adhesion to, but then also we're seeing some more variable manufacturing tolerances. And what I mean by that is that bond line thicknesses are changing, or we're being asked if we can apply things that thicker and still maintain the same performance, for example. So making sure we're taking all of that into account as we're developing some of these new technologies. And of course, with new requirements come new challenges that our technical team has done a great job of innovating around. So I will start kind of talking with our structural adhesives, and then I'll move on to our anti-flutter sealer developments towards the end here. So on the structural adhesive side, we do have an expanded bake portfolio now. Actually, a PPG colleague of mine did talk a little bit about our structural adhesive development work at this conference a couple years ago. And I just wanted to kind of expand upon that, how we've broadened that platform since then, and also moved on to anti-flutters and sealers as well in this space. So for the structural adhesives, this is going to be a 1K epoxy platform, really tailored to meet different strength requirements depending on where it's being applied within your vehicle. So a rigid, a crash, or a high crash adhesive, all of those are commercially available. And there were kind of a couple key technical innovations that were required, key focus areas for our team to enable this platform. The first being the reactivity and then the moisture resistance. So on the reactivity side, that's really targeting that low temperature cure. So you need to have a more reactive system in order to get cure at 140 C, 10-minute bake times, if that's your minimum cure target. And you can achieve that with different accelerator packages, right? However, what we found was once you do that, you get a more reactive product, you actually lose shelf stability. So that's not ideal. And so the team has spent a lot of time working on optimizing that accelerator package so you can achieve that low temperature cure while maintaining that long-term shelf stability that you would need. So here I'm just showing a basic graph, a DSC graph showing heat flow versus time. So you're really just seeing, you can change your accelerator, tune that reactivity, or find a balance of reactivity so you can enable those two different properties. On the right side, as we're developing these low temperature cures, we need to make sure that we have the mechanical performance that you would need, right? Both before and after aging. And on top of that, if we're taking into account potentially needing thicker bond lines, especially for structural adhesives, we've seen from typical 0.2 millimeters closer to 1 millimeter. You can see my highly sophisticated graphic showing that as you increase the bond line, you're going to have more susceptibility to moisture. So you really want to make sure you're increasing your hydrophobic barrier, so you're getting more moisture resistance. You get the same mechanical performance after humidity or exposure. And we're predominantly measuring that using lap shear strength. It's a fairly basic technique. I'm sure many of you are very aware, but essentially you apply a bead down with your two substrates. You apply a load across that, and you measure that failure mode, typically looking for a cohesive failure, so failure within your adhesive. And we want to maintain high lap shear strength after humidity exposure with these thicker bond lines, whether or not it's cured at 140C all the way up through the higher bake window. So just showing with these two innovations, we were able to enable these different properties, and I'll just show some of the data that supports that. So this is our crash adhesive, just showing some of the storage stability that's been achieved. So you can see we have accelerated aging, so that's just tracking viscosity over days of storage at high temperature, in this case 35C. You can see with that orange curve, that's not what you want to see, where you're seeing a big viscosity climb pretty quickly at high temperature. And we were able to formulate around that to bring it down to more close to that green line, where you have a really good stable viscosity over time. Of course, you want to translate that to real life conditions, so that would be more of a room temperature storage. So we did measure, this is a viscosity versus shear rate curve, just showing performance at 1 week, at 6 months, and at 9-month room temperature storage of the material. You can see very similar behavior between all three of these time points, that really nice shear thinning behavior. You would want very minimal increase in adhesive viscosity over the course of that 9 months. So we were able to achieve both heat age as well as long-term shelf stability for this product. On the mechanical property side, I'm just showing some representative data here for our crash adhesive. We also have a high crash that has even higher strength performance, but focusing on the lap shear strength first. So this is looking at a 1 millimeter bead, making sure we have really good lap shear strengths before and after exposure and within our full cure window. It's a little bit of a complicated graph, but essentially we're just showing before and after some optimization. First, initially at 10-minute 140C cure times, and then at this kind of more overbake condition at 200C, 20 minutes. So you can see in the blue, we had maybe not quite the lap shear strength that we wanted for that 140C cure. We were able to boost that up to above 25 MPa. After optimization, you get a little bit of a trade-off at the overbake condition, but still well within the range that would be acceptable, at least in the bounds of this particular request. And then we looked at a couple of different aging experiments, and without going into too much detail, it's essentially humidity and heat aging cycling. Aged 1 would be after cure, and aged 2 would be looking at heat and humidity exposure both before and after cure, so much more aggressive test. And you see a little bit of trade-offs in that performance as well, but within the noise, I think, and we get good improvement at that, especially at that 140C after optimization for that first aging condition. So while we're doing all that work, trying to balance those properties in the lap shear strength, we also want to make sure we weren't affecting the impact strength, right? Very important for crash performance. This is just a typical impact wedge test you can see on the right. Before and after optimization, we actually were able to improve the impact strength as well with this. So we were not negatively impacting that performance. Okay. This is a summary then of where we are today with our expanded bake platform. So again, 1K epoxies, we have a range of different adhesives. We have a high crash, a crash, and with a hem flange capability as well as a rigid. You can see kind of the step down in strengths that you can get depending on the specific requirements. For the high crash, just wanted to call out, we've spent a lot of time innovating around that frozen state impact resistance, so at negative 40C, making sure you get above 15 newtons per millimeter strength there. All of these products would have that 140C cure in 10 minutes, minimum bake, with long-term storage stability. Okay, so that's on the structural adhesives, and then I want to talk a little bit about anti-flutters and sealers as well. So we do have a technology platform for anti-flutters and sealers that's rubber-based. It has variable elongation and expansion depending on the specific needs. The two major focus areas for the technical team for this development was on the stability, which is obviously related to the reactivity we saw with structural adhesives as well, and then elongation. On the stability side, so we have to enable that low temperature cure, right? So thinking about tuning that accelerator package like I mentioned before, while maintaining that shelf stability. You also need to think about process stability, so that formulation robustness. We really need to optimize the binders as well to make sure we get good process stability throughout that cure. Window formulations throughout that cure window, and then over time as well. And that just comes down to, in a lot of ways, binder molecular weight. So can we tune different binder molecular weights to achieve that kind of stability that we need? On the elongation side, so thinking about flexibility and ductility, how do we adjust that depending on, again, the need, specific need, the location of where it's going to be applied on the vehicle, if we need a more of a sealing functionality versus like a high elongation functionality or a gap filling functionality. And really you can achieve that by adjusting the polymer microstructure. So just showing a very basic chemical structure here, but you get the idea, where we can adjust that microstructure to tune that elongation. And we're primarily measuring that using a standard tensile test with those dog bones, where you pull them apart until they break. And we've developed this tunable portfolio where you can tune that elongation to meet varying requirements. So just to show a snapshot of some of the mechanical properties of this material, of these anti-flutter technologies. So pressure versus flow. So this is a graph showing pressure versus flow for our standard bake formulations, as well as this expanded or low bake technology formulation space at both 2 weeks and 6 months. And you can see that the performance is very similar for pressure versus flow. And that's very important for anti-flutters, especially when you need to have very consistent and tunable shaped stability. So you have a very specific diameter and height of your droplets that you might be wanting to apply, making sure that's very consistent over time. And so we're able to achieve that. And then on the elongation side, so this is just, again, that tensile test I mentioned, so we're showing strength versus elongation percent. You can see our initial formulations, we were maybe in the 20% elongation range, able to tune that up to 80 to 100% elongation, depending on the specific technology. So we were able to get that improved elongation, but while maintaining that good process stability as well. So just to summarize, we do have a full expanded bake portfolio now, so Zircobond structural adhesives, semi-structural hem flange, as well as our core seal anti-flutters and sealers, all of which can achieve that expanded bake window with that minimum 140C cure in 10 minutes and 6-month storage stability. And some other properties I didn't go into detail today, but that obviously are important too, would be sag resistance, corrosion resistance, multi-substrate adhesion, and then robotic application. So all of these products partner well with our new Ecoat developments to help enable those costs and energy savings that Paula mentioned in her part of the talk. Okay, so I just wanted to wrap, just kind of summarizing, Paula introduced all these market trends and drivers that we're looking at and developing around, and I think our Ecoat and A&S expanded bake solutions really tie into a lot of those today: productivity, powertrain diversification, sustainability. But I wanted to also tease kind of what's next. And so thinking about that paint shop of the future, all the buzzwords: modular assembly, mega casting, giga casting, et cetera, making sure that we're positioning our portfolio to help enable those newer manufacturing processes. So we are looking at new solutions there. So we have a variety of ambient cure adhesives and sealants, some of which are commercially available, some of which are under development, that I wanted to just mention. Again, within our Zircobond structural adhesive product line, thinking about maintaining impact and shear strength that you would need with that ambient cure. And then we have a core seal structural sealer that we are working on, which would be balancing strength and elongation, so high strength and high elongation. So happy to talk more about that offline if that's of interest, but wanted to throw that out there. And then on this more substrate protection side, we do have a new aluminum pretreatment line that's specifically designed to improve efficiency within aluminum pretreatment space. So as we're starting to see more aluminum parts come online for lightweighting and other things, we have a product line that can help enable that as well, predominantly for our tier segment. So that's all I had. So I think thanks so much, everybody, for listening, and happy to answer any questions.
Okay. Again, if you want to submit your questions on the app or raise your hand. Any questions for Paula and Lindy? Okay, I'll get us started. Did you guys face any challenges? So you've got two developments happening. You've got your Ecoat development and your adhesives and sealers, and they have to play nice with each other, right? So how did you handle this kind of parallel path where you got to make sure that you're not formulating an Ecoat that can't tolerate a little bit of contamination from those sealants and vice versa? So were there any challenges with that?
Yeah, so I think I can start, Paula, if you want to add. So I think PPGs well positioned there, right? So we have all the layers, and I think that's a big advantage. Like, so we have our Coatings Innovation Center in Pittsburgh, where all the folks sit right next to each other, right? They're all in the same building. I worked there for a number of years, and I think that's a big strength. So like our adhesive and sealants team can walk down the hall and say, hey, what are you doing in Ecoat? What's your latest test results? Those types of things. Of course, you always have to make sure you're doing that, regularly checking in, keeping up with the new innovations, but I do think that we're well positioned to handle that. And then as we're seeing new challenges emerging, constantly reporting out to the team so we can take that back and say, okay, they're seeing a change in Ecoat, how does that impact our ANS? Do we need to make a change to accommodate?
I'll do one online more. Are you looking at going even lower in process window for Ecoat, whether by reducing curing temperature or bake time or both? And what are the main technical limitations?
Yes. And to Lindy's point earlier, we have to keep, anytime we go lower, Lindy is usually my first phone call. Because again, to her point, it's a process. So if I go in and I say I want to go down to 130 because we have a customer who wants to go to 130, and that is a big market trend right now, her ANS has to do that too. Or if we don't have that communication, then think of it as a process. We have to add ovens, right? Because then you have to cure them at different temperatures, and we don't want to do that. Our customer doesn't want to do that. So for us to go to 130 first, I have to consult ANS, and then we have to look at the resin, because again, what can we get out of the resin? What can we get the resin to do? How do we get it to cure by still being able to flow? We don't want to add a lot of additives because that adds cost, and that adds a problem with our Chinese OEMs. So yes, everybody wants to go to 130, and at some point we'll get to 130 and they want to go to 120. We'll get to 120 and everybody wants 80 to 90 for a 5 wet, right? That's what we do. But I think we're in a really good spot right now. I know we're not able to talk about it, but I think we're in a really good spot. I know ANS, and we have weekly meetings about it now. So yes, we're going, and we'll probably have a lot more to talk about it in Focus 2027.
Thank you for interesting work. So I'm from the aluminum supplier, Constellium, for OEMs. So we supplied a lot of aluminum sheet for the structural outer applications. So we are also monitoring this research and development in the PPG. During the curing of pen bake process, aluminum substrate also experience the change to meet a mechanical target. So it's an essential step for aluminum structure. So have you, this is a part of the consideration when you are like lowering the curing temperature. So for aluminum, from 180 degrees C down to the 140 degrees C is a huge change in the mechanical property. So we are interested so how to have OEM to adopt this technology.
So OEMs, and I'll speak from the Ecoat side, and then I'll let Lindy handle ANS. We already have a lot of OEMs that are already pushing to 140, right? And I'll be honest, from an Ecoat perspective, it's a lot easier for a line to handle 100% aluminum than it is mixed metal. So we see the issue a lot more on tiers, where a tiers line used to be, 100% carbon. And then all of a sudden it went to 80, then 60, and now you're down to 40 because they just keep packing more aluminum. And what happens is it generates a lot of sludge. So that's why a lot of our aluminum products usually, our pre-treats, our new technology that's more centered on aluminum will go to tiers first, and then we'll move it over to OEM. And that's very deliberate because it's a lot harder in tiers because they do a lot of mixed metal lines. But when you have a straight aluminum line, it's a lot easier to manage because you don't have this continuous sludge generation that has to be dealt with. So it's a little easier on the OEM side to go to lower temperature than it will on tiers.
Yeah, I'll just add, and I think, Paul alluded to this too, is one thing that we are seeing for current customers a lot of times is they're not actually dropping the temperature. They're just increasing their line speeds. And the lower broad bake window helps prevent cold spots, for example, of the adhesive. So you get full cure at the low temperature, or make sure if you have a heavier metal segment, you're still getting full cure of your adhesive or your Ecoat technology at the faster line speeds. And that is due to the complexity of things like other things that have to cure in that oven, like baffles and bake-hardened metals and things like that. So we're seeing innovation in those spaces as well, but that's why I think we're seeing more of that higher throughput as being the initial push for this.
Okay, we'll ask another one from online. Industry has moved from 2K adhesives to 1K, but is there anything that formulation chemists could achieve again with 2K adhesives for an expanded bake Ecoat to an actual low cure Ecoat for future throughput? So, yeah, 2K versus 1K, let's start there.
I used to make 1K. Do you want me to answer that?
Yeah, you can. Let me give it a start, please add in. Yeah, so I think for PPG, our focus generally for like oven cured systems, we're focusing on 1K technologies. There's a lot of simplicity in equipment, right? With a 1K versus a 2K, it's a technology that's tried and true. We believe we can reduce the temperature and still get good performance. For like an ambient cure though, now we are thinking 2K, and there's a lot of complexity there, right? In terms of new equipment, making sure you have the right mix ratios. But we believe that 2K, you have a little bit more control over the reaction than you would with like a moisture cure 1K, for example. So I see 2K more for like an ambient cure type technology system, which would be for maybe a more disruptive type manufacturing practice, or if you need more plastics on your line. So I think that's kind of where we would position our portfolio. Hopefully that answered the question. But Paula, if anything else to comment.
From like a 1K, and I know you and I kind of joke about it a little bit, 1K is dominant in a lot of areas except automotive. Where you have construction moisture cure 1Ks, and now people are making a polyaspartic 1K, right, modified. I always call it spar because I'm not going to call it a spur because I think of something else when I think of that. So to Lindy's point, we'll get there, and I think it just is going to depend on what technology or what chemistry is adopted to get there by us and our competition.
Okay, another one online. Is there an impact on target film thickness with the Epic Low Cure Ecoat product?
So we actually have a wider range because our friends in EMEA, I'm global, so I have to worry about everybody. Our friends in EMEA have their target is much lower than what I call ASCA, America is. It's about half. So the range, like 35 to like a standard. We have some OEMs that want to go down to 30. We have one that's like, can we do 28? So we're even looking at that. So we're going to go pretty low on this product if we can, which we will.
Other questions? Okay.
Yeah, let's go ahead and thank the speakers.
Thank you so much.